Okay, everyone, I'm JMNS I'm some random guy from the internet who does Lightning and Bitcoin stuff for some reason. And currently I work for C equals. We're making an LSP. And I'm not going to talk about anything related to LSPs right now. Rather, I'm going to talk about, multi-party off-chain mechanisms and a rather novel mechanism I created just last week. So, anyway, multi-party n greater than or equal to 2 off-chain mechanisms. So, when I say an off-chain mechanism is, for example, a Lightning channel. And a Lightning channel has 2 participants. So that's n equals 2. Now, what I want to talk here is what are the various off-chain mechanisms that we can use that have more than just 2 participants, that are beyond channels. Okay? So, this talk is going to be divided roughly into 3 parts. What the heck am I talking about when I say off-chain mechanism, multi-party off-chain mechanism? What's this? How are these things implemented? What is the actual mechanisms here that are involved? And so what? Why is this important? Why is this something that we should pay attention to? Why should you spend 30 minutes of your time in doing this, right? Okay. What? So this is a something like a classification diagram, class diagram, whatever you want to call it. So we have a cryptocurrency mechanism, which is a mechanism that allows you to transfer cryptocurrencies, or rather transfer economic value using cryptography. Okay? So a trust minimized cryptocurrency mechanism is one where you try to minimize the trust in some actor in order to be able to actually send and receive payments. So we want a trust minimized cryptocurrency mechanism because we want to be able to reduce trust, because trust is an attack vector on you. If someone betrays your trust, then you've been attacked. Okay? So we want to minimize this trust as much as we can so that we don't introduce an attack vector. So among trust minimized cryptocurrency mechanisms, we have proof of work blockchains, and we have multi-party off-chain mechanisms, which is what I'm going to generally talk about. So we know what a proof of work blockchain is. A proof of work blockchain is something like Bitcoin, where you have a list of blocks, and that list of blocks is, each block contains several transactions, and those transactions define how the state of the system changes over time. And the proof of work here is there to ensure that there is an incentive to keeping this list of blocks stable. Like, it's difficult to just reverse any of these transactions, because in order to reverse it, you need to repeat previous proof of work. Okay? And then we have a multi-party off-chain mechanism, which is something that is not a blockchain. Of course, that's why it's off-chain, involves multiple parties, and is a mechanism to transfer value between individuals or between participants. That's why it is a multi-party off-chain mechanism. So here, this is not a dependency tree. This is not, so obviously, existing multi-party off-chain mechanisms require a blockchain, but there's no arrow from the off-chain mechanism to blockchain here. These are instead classes or types, or C++ classes, whatever you want to call them. Okay? So among the various multi-party off-chain mechanisms, I guess the most famous is Pundrija and Decker-Russell syndicate. And then there's
31 hours.
It's a long time. Okay. Decker-Wadenhofer, and of course some of the older ones is one of the earliest channel mechanisms or off-chain mechanisms is the Spillman channels from Jürgen Spillman. So this is what I'm going to be talking about, is roughly this part here in this diagram. Okay? So we're not going to talk about blockchains, we're going to go over multi-party off-chain mechanisms a bit. Okay? So first let's digress a little bit. So we have a special term for multi-party off-chain mechanisms that have exactly 2 participants. We call them channels. So why is this kind of special? why is this special? I think, therefore I am, it implies that you exist, I exist. That's what I think, therefore I am means. So I exist, I know that I exist. And then everything else that I'm thinking about is the external world. So inherently here, from basic philosophy, you have two participants, yourself and the rest of the world. That is why channels are kind of special, because as long as you can ensure that you have some channel to the rest of the world, then you are now able to communicate with the rest of the world, you are able to send value to the rest of the world. And that's why two-party mechanisms like channels are a bit special. Okay? Now, the idea here is that you are alone and there's the rest of the world, because you don't know if the rest of the world is just a matrix, and I don't even know if all of you are real, right? So, but maybe I am not alone. Maybe you are an actual human being. Because I'm a human being, right? Everybody knows I am a human being. I have human body here that's waving its hand. So therefore I am a human being, right? So maybe you are human beings too, instead of shadows in the Platon's cave, right? So, okay, that's just why you have to consider mechanisms that are more than just two-party. The consideration here is that maybe these are other people who are actually real and not figments of the rest of the universe, who are like me, who are peers, that also have the same problem, the same issue with scaling. Like, as we know, Lightning doesn't scale because in order to onboard 8 billion channels, we're going to take how many years? Is it 40 years or whatever, right? So maybe I am not alone here, and that maybe there are actual other people. Maybe there are 8 billion other people who need to go onto the Lightning Network and get them on board. But of course, they're not going to fit all of that into the blockchain. Okay, so that's one part here. The other part is that I am going to discuss end-of-end mechanisms. Okay. So the important part here, again, is that we are going to drop down to this situation where everyone else in the same mechanism might not be separate individuals. They may be soft puppets of a single, very powerful entity that is, trying to fool you. That is why you need to have an end-of-end signature. You need to be part of this signing set. This mechanism needs you to participate in it. If it's able to kick you out, if this is K of N, then if the other K participants there are actually sock puppets of a single powerful organism or a single powerful entity that is not an AI and definitely not me, then it's able to kick you out and steal your money. Okay? So this N of N means that this is a consensus. Everybody has to agree, right? So this is a consensus system. Okay? Okay. So what are the various, off-chain, multi-party off-chain mechanisms that we have? So there's Spellman, that's Jeremy Spellman's, single directional channel mechanism. There's TABconf, which was actually published at around the same time as Poon Raija, but I think maybe a little later. But it wasn't used for Lightning Network because it requires a varying amount of delays on the unilateral close case, and it requires several transactions, so it wasn't really implemented. And we have Poon Raija, which is what Lightning Network channels currently are. And then there's Decker-Russell Asuntikun, which is more commonly known as L2, ELTOO. Okay, so each of these mechanisms store a state. So there's a state here. So what is the state that is stored by these mechanisms? So similarly to a blockchain, the blockchain stores the state of the unspent transaction outputs. That is the state here of the blockchain layer. So the set of UTXO's unspent transaction outputs is the current state of the system of blockchain system, and when you post a transaction on the blockchain system, that is a request to delete some of those UTXOs and insert new UTXOs to the UTXO set, right? So basically, similar to that, off-chain mechanism, a stake is a set of contracts who controls what of monetary value. So similarly, a UTXO in the blockchain, Bitcoin blockchain, is a set of contracts, a set of Bitcoin scripts that describe who controls some amount of money. Okay? So these things like Spellman, Dr. Wattenhofer, Brundreiche, Dr. you can find them on the internet. There's lots of discussion about these. These are rather old things. The youngest of these is like 5 years old by now. So you can find lots of information for them. Now, the thing what I want to point out though is that the Brundreiche has a revocation scheme. What this means is that if you use an old state, then the old state will be revoked. And the revocation path means that the other participant in this channel gets to get all the money in this channel, this mechanism. That is the mechanism that prevents old state from being posted on chain. So the problem here now is that every contract inside the state of this mechanism needs to include this revocation path. So it's infected with the revocation path. Now the other one is L2 or tailor-made. It infects contracts this time with the SIG hash formerly known as no input. Now the SIG hash formerly known as no input is the problem here that why it kind of affects contracts now is that the latest plans for the SIG hash previously known as no input is that it has to air a flag on the tap leaf version which indicates that yes, we allow SIG hash no input. Okay? But so it means that currently the latest plans that I am aware of to enable this SIG hash no input is that, okay, so taproot version C0 is the normal taproot path. That's all taproot scripts have version C0 for their taproots. However, the proposal is that if you use taproot version C1, that allows the use of SIG hash no input. Okay? So there is a flag there hidden inside the taproot version which indicates yes, allow any private out. And L2 requires any private out. Okay? Okay, so now I mentioned about the infection of Brundreiche. Okay? So it infects some contracts with a revocation path. Okay? So this is an example of how it looks like. Okay? So on chain, we have a funding transaction. This is a funding transaction output. The funding transaction output is simple 2 of 2 multi-signature requirement. That's a contract that allows this to get spent. Off chain, we have a transaction that spends this and gives the funds back to A and B. However, in this example here, this transaction is the commitment transaction that is held by A. So if A publishes this, there is the CSV time period in which this fund is locked on chain, and B can come online and say, hey, this was an old state, we already revoked this. And that is why there is a revocation path here. So that is what I mean by an infection. Ideally, if you want to look at it, the channel has funds for A and B, for Alice and Bob, right? And ideally, the transaction will have a contract that's simply A and simply B. But in this case, it gets infected with this revocation path because it's part of the things that are necessary to ensure that the off-chain mechanism works as advertised. Okay? So in order to disinfect Brundreiche, you can do something like this instead. Now, I want to point out that this idea is not original to me. This has somebody published a paper on this. Actually, it had 6 authors, so I don't remember all the names. Where, you know, they just kind of rotated the CSV or the revocation path requirement. Okay, so rather than here in the previous slide that we have the single commitment transaction, and immediately we split it out to the various funds in our current state. We have a some kind of a holding mechanism here, or holding UTXO here, transaction output here, which contains a revocation path. And then, if this is not challenged by B, then you can now publish this transaction here. And this transaction here has these simple direct contracts. So that's how we kind of disinfect Undraija. Now, the issue now here is that because there's a relative lock time here, if there are absolute lock times in your state, like for example HLCs, then you need to kind of drop this on-chain earlier by the CSV timeout, okay? As opposed to this style where each output can be revoked individually. Then if you can wait until just before the HLC times out and then drop it on chain, okay? This structure is actually similar also to what is done in Decker-Russell Asuntakun. So you can say that this is like the update transaction of L2, and this is like the state transaction of L2. Okay? Now, Undraija still remains a two-participant mechanism because it uses punishment. So basically, you cannot extend Undraija to 3 participants because of the punishment mechanism. Who punishes here is the one who gets all the funds in this mechanism. So let's say you have 3 participants in a Undraija. You set things up so that one of the other 2 can punish you. So for example, let's say A, B, and C participants. So you are A, right? And then B cheats, but you were offline at that time, so C does the punishing. So it gets all of the funds, right? The problem here now, how is it going to return back to you? What if B and C were colluding with each other? What if B and C are soft puppets of each other? Right? Because remember, everything drops down to 2 participants. You against the world, right? Okay. So Undraija remains 2 participant, so we know one. Now, we have Decker-Russell Asuntakun, and this one requires SIG hash, formerly known as no input. Okay? Every update and state transaction is signed with SIG hash no input. The state TX has no fixed transaction ID because it is pending an update transaction. And the update transaction could be different, right? And in order to generate the state transaction, you need to have a previous TX out, which is the TX ID of the tenure code spend, which means that you don't have a stable transaction ID at the state transaction. Then to spend from the state transaction output, you also need to sign with any prep out. At least as long as everything is off-chain. Once it's gotten dropped on-chain, then the transaction IDs have already been confirmed. Those are numbers are fixed now. You don't need to use SIG hash no input anymore. Okay? So this also implies that address use is bad. Why? Because the signature does not commit to a specific transaction. So if you have 2 contracts with exactly the same amounts and exactly the same, contract, if you have 2 outputs, transaction outputs that are exactly the same address, Bitcoin address, and exactly the same value, then a SIG hash no input, spending one of those can also spend the other. So any prep out means that address reuse is bad. So as I mentioned, the most recent, SIG hash no input proposals require a flag. So the last information that I had was that there would be a special tap leaf version that would enable the use of any prep out, SIG hash no input, okay? And that would be version C1, whereas normal tap would have tap leaf version C0 for its scripts. So because everything in the Decker-Russell Asuntakun requires to be signed by SIG hash no input, we need to enable it on every contract that we use inside a Decker-Russell Asuntakun mechanism. Okay, right? Clear? Good. So what? Okay, we can have multiple parties that are more than just 2. So n is greater than or equal to 2. For trust minimization, we want n of n signers because you don't know if all the other signers are even real people. Maybe they're just soft puppets of the same guy, right? Maybe, you know, you're inside the matrix and everything is fed to you. Okay? Now, the problem here now is that if you have end-to-end signers, all of them need to be online at the same time to change the state. Okay? That's the problem. Okay? So there's an onlineness requirement here. Now, this is not a blockchain. This is important because we know that blockchains stop at scaling. Okay? Every blockchain needs to be validated by all of the full nodes on the network. So that means that you have, let's say, n participants on the network. Those n participants are going to send approximately n transactions to each other, and that requires n squared transactions. And then you're now sending data, all of those transactions to every participant, meaning that the global bandwidth usage is n cubed. Okay? So blockchains do not scale. This is why Lightning is so awesome. Lightning does not require that every payment be published to every participant. It only requires that your payment goes through a route. And that route is going to be, you know, a tiny fraction of all the participants on the Lightning network. Okay? That is why it is important that we avoid blockchain mechanisms when we try to scale Bitcoin, because blockchains suck at scaling. Okay. Now, even though we have this mechanism, I will now show you that this mechanism can present an interface that looks a bit like a blockchain. Ta-da! Okay. Every magic trick has 3 acts. Okay. So what? So let's say that we have this starting state. So we have an off-chain mechanism. Let's assume that we have an off-chain mechanism that supports multiple participants, and we're going to use SIG-hash any prep out because, you know, SIG-hash any prep out is awesome. Okay, so let's have a starting state where we have 3 participants and they have their own funds, A, B, and C. Okay? Now, suppose this is the starting state, but now A wants to hand over some of its money to B. So what it can do is it can simply create another transaction, spending from its UTXO, and create a new A2 output, which is the change output, as well as a new B2 output, which is going to B, to Bob, right? Now, this transaction is not yet confirmed because A can sign a different version of this transaction, right? So it's not confirmed. You can consider it as an unconfirmed transaction that is in the mempool, right? Okay. Now, how do you get things confirmed? So to get things confirmed, you now have to gather everyone in this mechanism and say, this is now our new state. Sign off on this new state, and now we have this transaction that used to be unconfirmed in the mempool and is now confirmed inside our mechanism. Okay? This is because previous states, we have this mechanism that prevents previous states from being published. So whether that's by punishment or by replacement, like in, Decker-Russell Sutakun, or by using variable NC relative block times, like Decker-Wattenhofer, doesn't matter, we can replace this, right? Okay, so as long as we can be assured of the fact that previous states are invalidated, they're not going to appear, and if they do appear, we're going to be able to fix things so that only the latest state appears or whatever, then we're fine. Once it's gotten confirmed, once we've transitioned to this new state, we've gotten it confirmed. So this is an interface similar to a blockchain. You post it on the mempool first, and then you will wait for everybody to gather together, and then say, okay, we're signing it now, and now we have a new transaction set, we have a new UTXO set of outputs that can be spent now. And we are now sure that this cannot be reversed anymore. Okay? Now, it's possible for confirmation and this mempool mechanism to be asynchronous. So, for example, let's say that everyone gathers and says, okay, we're going to get this transaction confirmed. And then B suddenly wakes up and says, oh, hey, I got these new funds and I want to consolidate my funds now. So everybody can first agree on this. And then they start doing the signing mechanism. They start going, oh, let's do this music too, blah, 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 whatever. And then there's that, of course, that's not going to take 0 time. And because there's participant communication that's required here to get this new confirmation, whereas this one only requires B to sign for this transaction, right? So this can happen in parallel to or asynchronous to the confirmation of the previous state or confirmation of previous transactions. Now, the thing is, if you're going to move from this old state to the new state, then obviously these arrows here would need to be reseated to the new state, which is exactly the problem that SIG hash no input fixes. Ta-da! Right? Okay, so after you confirm this previous transaction, this one is still floating in the mempool, but you can now receive this transaction because the signatures do not commit to a specific transaction ID. Okay? They only commit to the contract and to the amount. Okay? So yeah, this is basically how it moves from this previous state to the next state. So the mempool here can operate asynchronously with confirmation, right? Okay. Whew. So, as I said, the mechanism requires onlineness. All of the participants need to be able to exchange those signatures to confirm the new state, right? Maybe the signatures can be intermittently online. Like, for example, like everyone commits, at 12 noon UTC, everybody has to go online and sign the new state. That now has to be confirmed. So it doesn't need, the mempool mechanism of this mechanism doesn't need to be stuck. You can just keep adding transactions there. Although, of course, since they're not confirmed, then they are, you can't rely on them unless you trust the sender to not double spend it out from under you. Okay? So for trust minimization, the signatory set is the participant set, which means that if you have an N of N signature, if you have money here, you have to be one of those N signatories. Okay? But as I pointed out, the interface here is similar to a blockchain interface. You put a transaction on the mempool, and then you get this confirmed, ta-da! So, what is next for this kind of mechanism? Okay, this is kind of new stuff that I just, thought up last week, literally. Okay, our reuse is awesome. Anyway, okay, can we create a special actuary that only fixes transaction ordering? So this actuary would be able to operate this off-chain mechanism, and it's going to say, okay, this transaction is now confirmed by signing off on that transaction. However, we want it to fix transaction ordering, which means we do not want it to support double spends. So what we can do here is that when we need to force it to sign only once. So if it tries to sign again to a different version of a transaction that it already signed before, then it has to get punished. It has to lose something. Okay? So what we can do is we can force our reuse. Like, for example, the contract includes, it needs a signature from the actuary. But the actuary signature needs to have an R that is this specific value. If the R isn't this specific value, then this is not going to be, valid on the blockchain layer. Okay? So our reuse, hi Nifty, our reuse is awesome, right?
5 minutes. 5 minutes.
Our reuse is awesome because it allows you to force sign only once on the actuary. Okay, the actuary is there to assure someone that this is already confirmed. I double signed it for your behalf. When I sign it, I can't sign a different version of this transaction because I am constrained to sign only once. Why? Because the contract requires that I use a specific R. If I sign a different message, if I sign a different transaction with the same R, I will lose my private key, like what Nifty said earlier, right?
Okay.
Right. And if I have funds in this that are protected by this private key, then somebody else can steal it and I lose my bond. Right? So the actuary has a bond on the on-chain, on the blockchain layer, that is protected by the same private key. And if it tries to sign two different transactions so that they become valid, then it's going to lose that private key. Somebody else is going to know it, and then that private key can now be used to steal his funds away on the on-chain. And he loses bond, right? Good. So what does this get you? The actuary can confirm even if all the participants are not online. So when the actuary confirms this, when it signs out of that transaction, so we are going to infect every script with this. So if your script is like, for example, A, we're going to make a sign only once with the actuary or a CSV and A. So the CSV here is there to, in case that the actuary disappears. So if the actuary disappears, you drop the thing on chain and then you wake up the CSV, and then you can now spend using normal A confirmations, and those you can now use the blockchain name, right? But if there is an existing transaction that the actuary already signed out before, signed on before, then you can post it directly on chain without waiting out this relative time lock. Okay? So the actuary can now confirm transactions without being able to spend funds from under the participants. It is not a custodian. This is important. This is not a blockchain. There is no custodian. I'm not trying to hit something else, right? Okay, so this is a concept sketch. So what we really need is a sign only once mechanism or a sign only once contract. So one of the ways you can force sign only once is to force R reuse. And typically, Object-SIG expects that there is a single stack item that contains both R and S. What we can do is that we have R fixed, and then you concatenate it with the S that is given by the actuary. And that forces the actuary to use always this specific R. Or alternatively, we can have a new opcode that takes two items from the stack and then concatenates it together, and then that is what it checks against as a signature. Okay? So once the transaction is signed by the actuary, it is confirmed. And now there's just this long line of transactions that have been confirmed by the actuary, and then we can then, periodically, like once a month, all of the participants gather together and they cut through all of those transactions to make a new state. Right? And the only reason for doing that is to kind of roll up all of those transactions. Right? Okay, so, let's go back to this case. Does C need to know this transaction? C doesn't actually need to know this transaction, right? Because let's say we have an actuary. The actuary is the one that records all of those transactions that is already confirmed. So periodically, once a month, it's going to contact all of the participants and say, okay, come online now, and then let's all sign this new state, and this is the new state that I want to sign off. Carol, or Charlie, or whoever the C is, doesn't need to look at all those transactions that Carol is not involved in. It doesn't need to know all those transactions. It just needs to look, does the new state have the outputs that I expect to be there? Right? So again, here, what we're doing is we're reducing the bandwidth that is required, and that is already scaling, right? This scales better than having a separate blockchain that, is custodied by hash rate, right? Because this reduces the amount of data that the participants in this mechanism need to actually process. They only need to look, oh, this is the new state. Are the outputs that I expect to be in this state still there? Okay, then I'll sign it off. What if, the actuary, doesn't cheat Carol, but it cheats, Alice and Bob? Then Alice and Bob are not going to sign it, and there's no new state. And if there's no new state, then everybody can just drop things on chain and resolve everything there, right? Ta-da! Yeah. So, no custody.